In this lecture, we are going to discuss about a general purpose Turing machine, which is like a computer. Suppose we want to use a computer to check whether a given number is prime or not. Then first of all, we need to get a program for primality checking. That program needs to be loaded to the computer, and then you execute that program. When you execute that program, you have to give a number as input. Then the computer will run that program with that number as input and will produce the required output. See, now if you look at the computer as a machine, it is taking two inputs. One is the primality checking program, and the second one is that number which is an input to the primality checking program. Today we are going to see a very similar kind of general purpose Turing machine, which will take as input a program and an input to that program. Then the general purpose Turing machine will run that program on the given input to the program and will give us the result on running that program on the input. Very similar to what we discussed about a digital computer, primality checking program and an input to the primality checking program. And when we discuss about that machine, things will become more clear. And what that machine is called is Universal Turing Machine, UTM. And before we look at what is Universal Turing Machine, we need to recollect what we discussed in the previous lecture about unary encoding of a set. Consider a set which is the set of states in an automaton. Say there are m states. Then in a unary encoding where only the alphabet is 1, you can represent the states as this. The encoding of the unary encoding of the state set is represented as cap q or hat q. And m states are there. The first state is represented as 1, the second state is represented as 1 1 or 1 square. Likewise, the ith state is represented as 1 raised to I or a string of ones of length I. Now, if you look at another set which is an alphabet set of an automata, then here again unary encoding will be represented as hat sigma, and the first alphabet is represented as 1, second alphabet is 1 1, likewise it goes. Now suppose you want to represent the direction set in a Turing machine, there are only two elements. The left direction can be represented as 1 and the right direction can be represented as 1 1 or 1 square. And note that if q is the set, its unary encoding is denoted as hat q. Similarly, other sets as well. Now see that the unary string 1 1 or 1 square represents the state q2 if it is a state. If you tell that that is the unary encoding of a state, then it is q2. If you tell that it is representing an alphabet, then it is A2, the second alphabet. And if you say that it is representing a direction, it is R because the second direction. Okay? So a finite set can have a unary representation on an alphabet set 1 where the ith element can be represented by a string of ones with the length I. The ith alphabet is 1 raised to I or a string of ones of length I. it is represented as 1 to the power I. Now let us recall the definition of a Turing machine. This is what we discussed. No need to remember all the components, but this is exactly what we defined as a Turing machine. So in a Turing machine there could be finitely many states, finitely many input symbols, finitely many tape symbols, and recall that every input symbol is a tape symbol. That is always the case for any Turing machine. Every input symbol must also be a tape symbol, because the input symbols are also, or the input string is also stored on the tape, and that is why this requirement is there. Then the next component is the start state, which is an element of Q. Then we have transition function from the current state for the current tape symbol. What is the next state? What symbol is going to replace the current symbol, and what is the direction of move is a transition function. You can have finitely many transition functions. And next is the left-hand marker, which must be a tape symbol, let us say A4. And the next one is a blank symbol, again a tape symbol. Now what is next? Next is the unique accept state, which is a sync state, which must be a state. Similarly, the last component is again a state. So if you have unary encoding for the state sets, alphabet set, and the tape alphabet set, then you can have an encoding for the Turing machine as a whole. Now you look at the unary encoding for these sets. We saw that in a unary encoding with the singleton alphabet 1, this is the required encoding for the state set. 1, 1, 1, 3 ones, 4 ones, and 5 ones. The ith element is represented as I ones. Okay. Similarly, this will be the unary encoding for the alphabet set. For example, 1, 1 will be representing A2. Naturally, this is the unary encoding of the tape alphabet set. Now what is this small s? It is a state, and which is that state? Q1. Its representation is 1, and that is what you are writing here. The start state is the first state in the state set, is what it is representing. Now a transition like this can be represented as from the first state Q1. If you are reading the second alphabet, that is A2, then you change your state to the third state in the set, that is Q3. Here you have Q3, and you replace the current symbol, which is A2, with the first symbol on the tape alphabet, which is A1. That is what you have here. And the direction of move is the second direction, which is R. Now the left-hand marker is the fourth alphabet, so you will represent it as 4 ones. Blank symbol is the fifth alphabet, so you will represent it as 5 ones. And what is T? T is the fourth state, so it is 4, and R is the fifth state, so it is 5 ones. Now see that if you want to have an encoding of the Turing machine definition, actually no need to remember the names of all these states, because the first state, regardless of the name, will be represented as 1. The second state, regardless of the name, will be represented as 1, 1. Likewise, the ith state will be represented as a string of length I, regardless of what the name is. So it is enough for the Turing machine to remember or to represent or encode how many states are there? 5 is enough. If you say that 5 states are there, then these are the representations, unary representations, no doubt. The first state is represented as 1, second state is represented as 1, 1, etc. Similarly, if you know that it's a tape alphabet, no need to remember the names of the tape alphabets, just remember how many are there, 5. Then the first alphabet is 1, second alphabet is encoded in unary as 1, 1, likewise it goes. Now we can see that it is possible to have a binary encoding for a Turing machine, simple binary encoding. Now suppose you have this definition of a Turing machine, only 2 transitions are given. Now you can have a binary encoding. This is the binary encoding representing this Turing machine. What is it? The first component is saying how many states are there. So it is a string of length 5, meaning 5 states are there. Then which are the states? 1, 1, 1, 1, 1, 1, 4 ones and 5 ones. Okay, so you just want to encode how many states are there. Then the next component is the alphabet set, and that should be represented by how many input alphabets are there, 3. And delimiter between 2 successive components is 0, and each component is represented by a string of 1. Okay, this is the number of input alphabets. After the next 0 you will have the number of tape alphabets, it is 5. Then after a 0 you have the start state, which is 1, means the first state is the start state. Then after a 0 you have the left hand marker. Now you are saying the 4th alphabet here is the left hand marker, which is correct. Now after a 0 you have the blank symbol. You are saying that the 5th symbol on the tape alphabet, which is A5, is the blank symbol. Yes, which is also correct. Then after the next 0 you have the except state. You are saying that the 4th state here, Q4, is the except state. Then after a 0 you have the reject state. You are saying that it is the 5th state in the state set, Q5 is the reject state, correct. Then you have to represent a transition function. How many components are there? 5 components. Each one is represented as a string of 1s, and 2 successive components are separated with a 0. So this tells from the first state, that is Q1, for the second in alphabet, that is A2, change the state to the third state, that is Q3, replace the second alphabet with the first alphabet, A2 with A1, A2 with A1, and move right because the second direction. Similarly, the next transition function, from the second state for the third alphabet, change to the 4th state, replace this third alphabet with the 5th alphabet, third with the 5th, and move left. Okay, so thus we are getting a clear picture about what kind of a binary encoding you can have for a Turing machine. For any object, the binary encoding is represented as hat of that object. So this is what we have seen. For any Turing machine M, there exists a unique binary encoding hat M. Now we can also have a binary encoding for an input string in any alphabet set. For example, consider an alphabet set sigma with only 2 elements, small a and small b. Now of course you can have unary encoding for a and b. So a can be represented as 1 and b can be represented as 1 1. Now a string w on the alphabet set sigma can be represented using a binary encoding w cap or hat W such that the alphabets in W are represented in unary, that is 1 and 1 1, and the successive unary representation of characters are separated with a 0. Look at an example to understand. So W1 is AB, A is encoded as 1, B should be encoded as 1 1, and between these encodings you can have a 0. So it's like the unary encoding of A followed by a 0 followed by the unary encoding of B, followed by a 0 followed by the unary encoding of A, followed by a 0 followed by the unary encoding of B. Very easy to obtain reversible transformation. BAB, what should be that? 11011, right? Sorry, 110, this is represented by 1, then after this 0, then 1 1. The last example, BAAB, how will you represent it? 1 1 followed by a 0 followed by 1 followed by 0 followed by 1 followed by 0 followed by 1 1. So this is exactly the binary encoding that you need. So the take home from this slide is that on any alphabet set, a string can be represented in binary, and the binary encoding of a string W is denoted as hat W. So this is what we have seen. For any input W, which can be an input to a Turing machine M, there exists a unique binary encoding hat W. Now we have got enough information to define a universal Turing machine UTM. It's a Turing machine U which takes as input what is hat M, the encoding of another Turing machine, the binary encoding of another Turing machine, and the binary encoding of an input to the Turing machine M. They are separated with a hash. So what the universal Turing machine is taking as input is a binary encoding of another Turing machine M and an input W to that Turing machine M. Actually it is taking a binary encoding of that input as well. So two binary strings separated with a hash. And what does it do? It accepts the input. What is input? Input is this. When the machine M accepts the input W. Okay. So the input to the universal Turing machine is a pair. What is that pair? Pair of encoding, binary encoding. The first one is an binary encoding of a Turing machine, say M, and the second one is binary encoding of an input to that Turing machine M. So this input is accepted by the universal Turing machine if this given Turing machine accepts W. Okay, and the input is rejected if M rejects W. So that is the universal Turing machine. You can see how the universal Turing machine works, that we can see in the next slide. So what is input? Input is a binary encoding of a Turing machine hat M followed by a hash followed by the binary encoding of an input string. If the alphabet set is AB, then it is ABAB, that is the input string. So the universal Turing machine U takes as input the binary encoding hat M of a Turing machine M like this, and binary encoding hat W like this, which is an input to the Turing machine represented by this binary encoding. See that here there are two Turing machines in the picture. One is the universal Turing machine and the other one is a Turing machine that the universal Turing machine is taking as input. Okay, and the binary encodings are separated with a hash. So the alphabet set, input alphabet set of the universal Turing machine is the binary digits and hash. on a given input, that is a binary encoding of a Turing machine and the binary encoding of a string to that Turing machine, what it do is the universal Turing machine will check whether the encoding given as the first part is a valid encoding of a Turing machine, and also it checks that after the hash it is a valid binary encoding of an input string. For example, you cannot have 0 zeros, right? Every 0 is preceded and succeeded with a 1. And actually this validity checking can be done with a finite state automaton, because you know that what is the valid encoding of a Turing machine? It is a sequence of ones. We don't know how many. Depending on the Turing machine, the number of ones may vary, but it is a sequence of ones followed by a 0, followed by a sequence of 1, followed by a 0, followed by a sequence of 1, likewise it goes. And here it stops, and then is the transition function of the same structure, so you repeat. You can verify it offline, but please take it as granted. A Turing machine can easily check whether the encoding is a valid encoding or not for both the Turing machine as input and the input to that Turing machine, which is again an input to the universal Turing machine. So this is the finite state automaton for checking the validity of the input string. So what should be that? A sequence of 1 followed by a 0, followed by a sequence of 1, followed by 0, likewise it goes forever. Okay, now forget about these details. What is it doing is, the universal Turing machine will run the Turing machine M on the input W, and what is it doing is accepts if M accepts W, rejects if M rejects W. And recall that there is one more possibility, M may loop on W. So in that case the universal Turing machine also loops on W. So these are the three possibilities. Accepts its input if M accepts W, rejects the input if M rejects W, and loops on this input if M loops on W. And now verify that what is the language of U, what is accepted. It accepts only if M accepts W, right? The universal Turing machine accepts only if M accepts W. Okay, so a string hat_m hash hat W will be accepted only if M halts on W. So it is the set of all inputs hat_m hash hat W such that W is in the language of M, or M accepts W. Okay, that is the language of the universal Turing machine. Now it remains us to check what is the structure of a universal Turing machine and how can it run another Turing machine on its input. This is the basic structure of a universal Turing machine. It is a 3-tape Turing machine. In the previous lecture, we discussed about multi-tape Turing machines, and it is known that multi-tape Turing machines are not more powerful than the standard Turing machine. They are equally powerful. So you can easily take a multi-tape Turing machine because a single tape Turing machine can also do it. But for simplicity in describing what it is going to do, you take a multi-tape Turing machine with 3 tapes. And what are its components? Here is the control unit of the universal Turing machine. Tape 1 storing the encoding hat_m of the Turing machine M. Not that, to the universal Turing machine another Turing machine M which is actually encoded in binary, and an input to this Turing machine or input to the universal Turing machine. If you recall, hat_m hash hat W is the input, where the hat term is stored in the first tape and hat W is stored in the second tape. Note that these are binary encodings. And what is the third tape? The third tape is storing the current state of the the current state of this Turing machine, input machine. The state of the universal Turing machine is maintained in the control unit, but this tape is used to represent or remember the current state of the machine M when it runs on W. So this example says that it is the third state, and after a 0 the next component says the position of the read write head of this Turing machine. Okay, and what this do is the universal Turing machine repeatedly performs the following to run or simulate the execution of M on W. And what is it saying? Scan the tape 3. When it scans the tape 3, it can find the current state and the current position of the read write head of the machine M. Okay. Now scan the second tape. From this it knows to which symbol this machine is pointing to, and that is the position of the read write head is known from here. Go to that position and see what input symbol is stored over there. Recall that it is represented in unary. So if it is I once, that means the ith input symbol. That's it. Now scan the tape 1. What is the tape 1 containing? The binary encoding of the Turing machine. So definitely all its transitions are stored over here. So now you know what is the current state of this machine that you read from here, and you read the position of the read write head from here. Using that you found the input symbol. So you got the current state and the current input symbol. So you want to now see the description of M to know what is the transition which is applicable. Now maybe the current state which is Q3 because it is 3, and the read write head was positioned at the second cell here or the second element here, and maybe that second element here represents the ith input character. Then you need a transition for AI from Q3, and suppose the transition is this. You change your state to Q4, replace AI with AJ and move right. You find that transition from here. Depending on the LHS that you have from here, you find the transition. Okay, so scan tape 1 and find the transition to apply in the current configuration of the machine M. Then what you do? Apply the transition. How can you apply? The state change can be recorded here because this is the place where the state of M is maintained. If it is 4 means you have to get 4 ones here after a 0 followed by the position of the read write head. Previously it was to the second input symbol. Now if it is right, it should be changed to the third input symbol. Okay, and also you have to replace the current input symbol with the symbol to be placed on that, and that you can do in the second tape. Okay, that is how it can simulate. So go and see what is the current state of the machine M. See where is the read write head position. Go to that position and see what is the next input symbol or next to tape symbol from here. Now you got the state and the next tape symbol. Scan the first tape and find the required transition. Then you apply that transition. Applying that transition requires you to modify tape 2 and tape 3 as required. Okay, I hope you are following, and keep on simulating it. And suppose the machine M executing W enters into one of the sync state TM or RM, the sync state of M, then the universal Turing machine also enters its accept state or reject state respectively. So now you can easily see that what we are getting is what exactly we discussed in the previous slide. With this we are finishing this lecture, and I am giving you a homework exercise for you to identify what Turing machine is represented by this encoding. Today we discussed about Universal Turing Machine, which takes as input the binary encoding of another Turing machine M and a binary encoding of an input W to the Turing machine M. Then what does it do is it simulates the execution of M on W, and if M accepts W, the Universal Turing machine accepts, and if M rejects W, the Universal Turing machine rejects, and if M is looping on W, the Universal Turing machine is also looping. So that is a Universal Turing machine. Thank you.